Hello everyone and welcome to MacTech 40, and today we are going to solve two questions of DRDO Means 2019 question paper, and both these questions are from paper 1, question number 7b and question number 8b. So first of all we will solve question number 7b, a very good question, and we can see that you have to just apply your concept. If you are conceptually strong then you can solve, otherwise you have to leave this question, but this is a very fantastic question. So let's start. A vapor compression refrigeration cycle uses R134A as a refrigerant. Okay. The state of the refrigerant at the exit of the condenser is saturated liquid at 55 degree. So here it is a, I have drawn TS diagram. So TS diagram, that is the, at this is the condenser temperature at exit, it is 55 degrees Celsius and it is a saturated liquid. So this is at 0.3. Now the exit of the evaporator, that is saturated vapor, that is at minus 25 degrees Celsius. So this point, and at this point, point number 1, saturated vapor, it is minus 25 degrees Celsius, and it uses throttling device for expansion and having refrigeration capacity 500 watts. So that means refrigeration effect R is equal to 500 watt. So we know that what is the refrigeration effect or refrigeration capacity. It is denoted by enthalpy difference into mass flow rate of this this from evaporation region. This is 4 to 1. Okay, and so we can say that 55 as a condenser temperature and 25 as minus 25 as a evaporator temperature, and corresponding to property table given here. So what we have to do is first sketch the cycle on the pH diagram. Yes, this is the diagram, pH diagram of the cycle that you can see here, and this is the way you can draw. And you have to show the arrows over here in which the cycle is moving, in which pattern cycle is moving. Similarly on TS diagram also. Now the twist comes here. If throttle is replaced with the isentropic turbine, that means here we are using throttling. Instead of that we are using turbine to get the some amount of work back, because in throttling we are losing that work. So but instead of this, if we are using that isentropic expander, that means this point, so this straight line there, and 4 point will now become 4 dash point, and this much, this horizontal red line area is the new increase in the refrigeration effect. Okay, so first of all we have to find the power output from the turbine, that is this new turbine that is we have installed, and new refrigerating effect after installing the turbine. So before that, how to solve this, how to proceed for this question. Before this we know the initial, that enthalpy at point 1, enthalpy at point 1, that is saturated vapor enthalpy at minus 25 degrees Celsius. So from this property table, whatever I am values taking, that is from this table in only. So that is 382.95 kilojoule per kg. And now H3 point, that is a saturated liquid enthalpy at 55 degrees Celsius, that has been same for H4, because 3 to 4 is a isenthalpic expansion, that is throttling. So that is 279.72 kilojoule per kg. Now we know that mass flow refrigeration effect R is equal to, given by mass flow rate of the refrigerant m dot into H1 minus H4. So refrigeration effect is 500 watt, but we have to convert in kilowatt, so divided by 1000. Mass flow rate of the refrigerant m dot, H1 is what, 382.95 minus 279.72. So when you solve this, you will get as a mass flow rate as m dot, that is 4.843 into 10 to the power minus 3 kg per second. So this is the mass flow rate. Now what we have to do is find out the turbine expander work, that means H3 H4 dash. So work from the turbine, so turbine work W turbine, that has been given by m dot into H3 minus H4 dash. This is the isentropic work. I am showing it on the TS diagram, this much, this vertical line, this much showing the turbine work output. So what is the H3? We have the value of H3, but we don't have the value of H4. And as you can see here, the H4 point, this H4 dash point here is in the wet region. So first we have to find the dryness fraction of it. So how to find dryness fraction? And we know that expansion of the turbine is isentropic. So entropy at point 3 will be liquid entropy is equal to same as the entropy at point 4 dash. So at 3 point, entropy of liquid is 1.2619 from this property table that has been taken as 55 degrees Celsius. And as 4 dash, that means entropy of the refrigerant in wet region at minus 25 degrees Celsius or evaporator temperature, that is SF 0.8457 plus X times HFG, SFG, H times SFG. SFG here it is 0.8687 given 0.8687. So solve this, you will get X fraction is 0.44. Dryness fraction is 0.44. So use this equation to X and to find out the enthalpy at point 4 dash. H4 dash is what? HF plus X times HFG at minus 25 degrees Celsius. So HF is what? From the table I have written the value 167.38 plus 0.44 into 215.57. So when you solve this, you will get as a 262.23 kilojoule per kg. Now turbine work. So we have a mass flow rate 4.843 into 10 to the power minus 3 into H3. H3 value we have already that 279. Here we already found out 279.72. 279.72 minus this value, that is we have found 262.23. 262.23. So this is the way, and when you solve this you will get turbine work in terms of watt, that is 84.7 watt. 84.7 watt, that is the turbine work output that you will get. Now new refrigeration effect. Refrigeration effect new Rn will be what? Mass flow rate into H1 minus H4 dash. How? Because in the TS diagram, as you can see that this region, this new added region as well as this old, this much is the refrigeration effect. That means the heat added in the evaporator section. So mass flow rate of the refrigerant is 4.843 multiplied by 10 to the power minus 3 into H1. H1 is what? 382.95 minus 262.23. So when you solve this, you will get as a refrigeration effect new, that is 584.64 watt. New refrigeration effect 584.64 watt. So this is the answer of the first question that they have asked. So I hope you'll understand this point. So where the sequence goes, I am writing the sequence. First we have find out the H1 H3, then refrigeration effect. From this mass flow rate, first we have find out, then dryness fraction, and dryness fraction we will find out. We have find out this from this dryness fraction we have found out the first this enthalpy at new point H4 dash. Then we have solved the turbine work, and after that we have found out new refrigeration effect. So this is the way we have proceeded. If anyone has doubt, then this is the arrow and this is our final answer. I hope you understand the solution. Now next question, that is a consider an A standard Brayton cycle with compressor whose isentropic efficiency is 0.8 and the turbine whose isentropic efficiency is 0.9. So compressor efficiency, given that compressor efficiency is 0.8 and turbine efficiency that is 0.9. Okay, all the other processes are idle, that means heating and cooling are idle. The compressor inlet at the air is 1 bar. This is this point. This is 1 to 2, 2 to 3, 3 to 4, and 4 to 1. So at inlet, so at point 1, P1 is 1 bar, and T1 initial temperature is 300 Kelvin. The pressure ratio, that is RP, is 30, and the maximum cycle temperature. So from this TS diagram we can see that the maximum temperature at point 3, so T3 will be 1500 Kelvin, and that this much data is given, and CP value is given 1.005. CP is 1.005 kilojoule per kg Kelvin, and gamma value, that is 1.4. And what you have to find, compute the pressure and temperatures of the states of the cycle and its thermal efficiency. That means we have to find at all the states temperature as well as pressure and thermal efficiency. So how to proceed that? So first of all, we will find the, as we know that heating and cooling, these both are constant pressure heat addition and constant pressure heat rejection process. So we P1 is equal to 1 bar, and P2 by P1 is a P2 by P1 is 30 ratio is given, pressure ratio is 30, so P2 is what, 30 bar. Similarly 2 to 3 is a process of constant pressure, that is 30 bar, and again P3 by P4 ratio, that is also same 30, so P3 is 30, so P4 is 1 bar. So P1, so in short we can say that P1 is equal to P4 is equal to 1 bar, and P3 and P2 is equal to 30 bar. Now temperature at the various points. So temperature at initial point and point maximum temperature point is given. So as this is 1 to 2, first if you take the isentropic compression, then T2 by T1, T2 dash, sorry, yes, T2 dash by T1, T2 dash by T1 is equal to pressure ratio power gamma minus 1 upon gamma. So here T2 dash we have to find out, and T1 is given 300 Kelvin, pressure ratio 30 power 0.4 divided by 1.4. So when you solve this, you will get the isentropic temperature, isentropic compression temperature, that is 792.78 Kelvin. But the compression and expansion are not isentropic. They have some irreversibility associated with it. So isentropic efficiency of the compressor is given by ideal work upon actual work. So what is the ideal work? So CP, sorry, and that is CP into T2 dash minus T1 divided by CP into T2 minus T1, that is 0.2 is the, as you can see this 0.2, that is the actual compressor exit temperature, and this 4 as the actual turbine exit temperature. So CP will get cancelled out. Compressor isentropic efficiency is given as 0.8. T2 dash we have, that is 792.78 minus T1. T1 is 300 Kelvin. T2 we have to find out, minus T1 is 300. So from this you can find out T2 as a 915.975 Kelvin. So this is the temperature at second point. Now from 3 to 4, so if you take isentropic expansion, then T3 by T4 dash is equal to pressure ratio power gamma minus 1 upon gamma. T3 is 1500 Kelvin, T4 dash pressure ratio is 30 power 0.4 divided by 1.4. So when you solve this, you will get the isentropic turbine exit temperature T4 dash, that is 567.62 Kelvin, 567.62 Kelvin. But the expansion is also not isentropic, so there is some irreversibility associated with. So turbine isentropic efficiency of turbine is given, that is called as given by actual work upon ideal work. So actual work is given by CP T3 minus T4 divided by CP T3 minus T4 dash, that is ideal exit temperature. turbine efficiency is given 0.9. CP will get cancelled out. T3 is 1500 Kelvin. T4 value we don't know, we have to find. Again T3 is 1500 Kelvin minus T4 dash, we have found out 567.60. So when you solve this, you will get T4 as a 660.858 Kelvin. So these are the exit temperature at all the 4 points. So now some major questions are done. Majority of all the questions have done. Now majority the things they will asked, that has been solved. Now only one thing that we have to find out in this case is remaining, that is thermal efficiency of the cycle. So if the Brayton cycle, air standard Brayton cycle with compression and expansion are isentropic, then the thermal efficiency formula is given by 1 minus 1 upon pressure ratio power gamma minus 1 upon gamma. But here there are some irreversibility associated with it. So we have to follow the some fundamental paths. So what is the thermal efficiency that is called for cycle? That is net work upon heat supply. So net work is given by what? Turbine work minus compressor work divided by heat supply. So turbine work is, we can find out here, turbine work 324. So we can write out Cp T3 minus T4, turbine work is given by, minus compressor work, that is Cp T2 minus T1 divided by heat supply. Heat supply, that is constant pressure heat addition, that means Cp T3 minus T2. Here you can say that this is the heat supply process 2 to 3, that is heat supply at constant pressure. So Cp T3 minus T2. So Cp will get cancelled out. So thermal efficiency of the cycle is given by T3 value, that is 1500 minus 660.858 minus 915.975 minus 300 divided by T3 again, that is I'm substituting the values of all the temperatures that we have. T2 value 915.975. So now if you solve this, so you will get a thermal efficiency of this cycle as 38.12%. 38.12%. So this is the answer of thermal efficiency of the cycle. And this is the end of our video. I hope you enjoyed this solution. If you have any doubt, then you can ask in the comment section as well as in the Telegram group also. So this is for today. Tomorrow we will meet with new questions. Till then, keep watching, keep studying, and like this video. Share this video with your friends and subscribe this channel for more this kind of videos and their notifications, so you will never miss this video. Thank you for watching.